Good. Yeah, so I'm Peter Watson from Bristol University. So kind of filling in for a speaker who had to pull out. I thought I'd take the opportunity to talk about why I think machine learning applications for weather and climate need greater focus on extremes in these studies. So from the perspective of myself being a kind of scientific user of these kinds of statistical machine learning methods, and one who's particularly interested in trying to understand risks from extreme events. So no, it's going to ding. How do I change the slide? Okay, fine. Yeah, so quite a lot of studies now have shown impressive seeming applications of machine learning. So we've had studies on things like numerical weather prediction, where we now have at least 3 groups who claim they can outperform the conventional state-of-the-art. And also like high resolution downscaling is another application area with impressive results. But we know very little actually about how any of these systems will perform for their extreme events, because those kinds of diagnostics are not shown. And I mean, I'd say that particularly claims of outperformance of anything are kind of premature before performance on extremes has really been evaluated. So why are predictions of extremes important? So it's going to be critical for any kind of general purpose system which may face events of unprecedented severity during its operation. So, for example, numerical weather prediction or in climate simulation post-processing. So, as an example, right, in last year in the UK, we had this storm Eunice, which had record-breaking gusts with return periods up to 200 years. So return period meaning like the average interval between times when you'd expect those kind of values to be exceeded. I mean, weather forecasts, right, are safety critical. They're used to direct emergency services. They're used to kind of warn the public to take mitigation measures. So we definitely want systems to be able to kind of stand up and keep performing well in these kinds of situations. So good performance on extremes is also very important for any particular research use cases. Focused on studying highly damaging events. So extreme weather attribution is an example in climate science. So an example study in this area was, or an example event studied in this area was Hurricane Harvey, where its kind of return periods were estimated to be in the thousands of years. And obviously to be useful to that kind of study, then any stats or machine learning method has to be kind of robust out to that sort of extremity. And I'll just say as a kind of side note that not all extreme impact events are so meteorologically extreme. So these points won't necessarily apply to all kinds of extreme meteorological impacts, but anything where you are really concerned about very rare, intense weather events, this will matter a lot. So yeah, so this chart just kind of illustrates what we all know about why we might be skeptical about machine learning methods' ability to simulate extremes well. So basically, you could get a system which, for the orange curve here, a kind of complicated statistical model which fits all your points in the middle of your distribution really well, but then at the edges goes pretty erratic. Importantly, right, you can't tell how it's going to perform at the edges by looking at the performance in the middle. You have to basically go out and do separate tests of what's going on these edge parts. And it'd be very valuable to know for advancing machine learning applications what kind of methods actually work well. So using like bigger versus smaller models, or using pure machine learning versus hybrids, or indeed using the kind of conventional statistical methods versus fancier, newer machine learning. This isn't something that should be done as an afterthought, which is the kind of approach being taken a lot at the moment. So if basically people put loads of effort into kind of fine-tuning systems to perform well on the kind of typical sort of weather events, and then it turns out, well, it just doesn't generalize well to extremes, and it's not very useful as a result, then I mean all that fine-tuning work would have been wasted. So it's something that really should come in. And you have an obvious first step when developing anything, like you get it working well on your kind of typical systems looking okay, and then the next step should probably then be to see, okay, is this actually generalizing well before you go and do loads of fine-tuning work. Yeah, so it's also worth kind of discussing, what is really meant by the term extreme, because this is used in lots of varying ways. So a lot of studies will kind of claim they look at extreme weather events, and what they really mean is something like the 99th percentile of daily data. So that corresponds to a return period of 100 days. And I mean, of course, looking at this kind of part of the distribution is valuable, but it's not getting at events which are really impactful. Like we don't have really impactful weather events of a particular type every 100 days. So when we're looking at the really most severe impacts, we're thinking more in the region of, say, 100-year return period. So in terms of daily data, that's the 99.997th percentile. We might also care about 1,000-year return periods. So that's, you get an extra 9 then. And you sort of see that thinking about this in terms of percentiles is not really that useful. It just becomes, a load of 9s in a row. So thinking about it in terms of return periods or magnitudes is probably more reasonable. This is just illustrating some numbers, just illustrating the kind of number of standard deviations out you have to go to kind of get to these sort of extremeness of events. So for a normal distribution, which might correspond to, say, temperature, and an exponential distribution that might correspond to, say, rainfall. So basically, we're talking like out to about 13 standard deviations for the exponential case, and the 100-year and 1,000-year events are roughly 2 to 3 times the 99th percentile. So that's the kind of magnitude that is worth thinking about for these kinds of applications. But it's important to note that even greater extremes do occur. So as an example, a few years ago, we had 30 standard deviation, 14-day average rainfall observed in the region in India. And in terms of flood discharge, river discharge, we've seen observed discharges up to 200 times the 10-year return level, which is really, really an extraordinary amount. I mean, to be honest, I'm not really sure I'd expect any forecasting system to be able to kind of simulate this kind of thing, but just to show that you can, even events of such high magnitudes do have practical relevance. So yeah, I thought I'd give an example from some recent work looking at performance on generalizing to extremes from a student at Bristol, Emily Vosper, who's been looking at doing downscaling of hurricane rainfall. So basically going from coarse resolution rainfall data sets to fine resolution trained on satellite data. So she tested 2 different types of generative adversarial network, and Wasserstein-GAN and the VAE-GAN. And for the kind of typical cases in the data set, they both do very well actually at reproducing the fine scale structures of rainfall, and the quantile plot of the core average rainfall looks very good up into the tail. But yeah, to look at how does this perform on extreme events, kind of more extreme than anything seen in training. We also did a test where we took out the 100 most intense hurricanes, held out as an extreme test set. So these weren't even used in the kind of model development process. These were not looked at right until the end. So on these, the Wasserstein-GAN actually still did surprisingly well at reproducing quite realistic structures. The VAE-GAN, on the other hand, starts breaking down with these. You get kind of weird artifacts in the 2D fields. And for the quantile plot, the Wasserstein-GAN still is very close to the ideal 1-1 line, but the VAE-GAN goes off and predicts some wildly higher values. So the Wasserstein-GAN's performance here is quite impressive, given that these values are something like 3 or 4 times what is seen in training. So it has still kind of learned to be able to go out that far. And yeah, I think this does illustrate the point that machine learning systems can at least sometimes generalize well to extreme events. It's not kind of some kind of lost cause, as some people seem to say. Yeah, do you want to? Yeah.
How dissimilar are these? Is this held out test set from training set?
How dissimilar?
How more
Well, yeah, about 3 or 4 times. Oops, sorry. It's about 3 or 4 times the kind of average rainfall over the thing. Yeah, so it's quite a large extrapolation actually. But yeah, so yeah, we can at least sometimes do well at these kind of extrapolation tasks, but you can get cases where it does illustrate a case where if you'd spent lots of time tuning this BAE for your typical events, you might just find that it just breaks down at your more extremes, and then it's not been a useful exercise. So another example from another Bristol student is so Henry Addison's work on doing UK rainfall downscaling. So the idea here is to train on high resolution simulation data from the Met Office's 2-kilometer UK downscaling model, and he's using a diffusion neural network to learn to predict the high resolution rainfall based on climate model data. So the same climate model data the downscaling model sees, and it's doing quite well at predicting realistic spatial structures of rainfall. And then yeah, this is showing a quantile plot of the events, showing a very good agreement actually with the ideal case. And in this case, this goes right out to the top of the data. So this is the very highest fine scale rainfall value in the data set, and this is using 108 years of validation data because we have loads of model data for this case. So this is just another another relatively simple way of being able to show that a system can actually perform reasonably for extreme events. Just something like a quantile plot, but including the most extreme values in there, so you can really see what's going on in the tail. Yeah, so in the paper that I wrote last year, I kind of went through a few other success examples that are in the literature, showing that machine learning, can at least sometimes perform reasonably for extremes. So yeah, a couple of these cases were this nice Gronquist et al. Paper where they looked at post-processing numerical weather predictions using neural networks, and actually got a fair amount of kind of improvement in the tropical cyclone Winston case, which was a very intense cyclone. And Frame et al. Studied prediction of river flows, showing actually improvements over the kind of conventional methods, even for events with return periods estimated to be out in excess of 100 years. But in total, I've only found like 7 studies to date which actually examine extreme weather events with return periods at least several years, which is a fairly modest threshold, and only 4 going out to the 100-year period or beyond. Now, you're not including Emily's case, which was kind of only recently done. Yeah, so it's notable that there aren't any studies apart from Emily's which kind of show a clear failure of machine learning systems in these cases. But it may just be publication bias, and we don't have enough samples of studies to really know in general how well this is going to work. So yeah, just to give some thoughts on kind of more useful diagnostics to show. So one is a simple one like scatter plot, going right up to the highest values of a data distribution. You can just very quickly visually confirm that the model is not producing anything wild. This is an example from Akani Adewoyan, who's a student here at Warwick, for UK rainfall. Something slightly more involved, but it would be good to see more, I think, are extrapolation tests. So basically, you take cases. You could say, for example, take a weather system that your machine learning is being trained on, and then just scale up the anomalies by some multiplicative factor, and just see how does it kind of handle the scaling up. What's this behavior like? This would be quite informative, probably, about how it's going to handle any more extreme events in future. So yeah, so that brings me to the end. So I've shown that machine learning does work at least sometimes for extremes, but it's been evaluated only in a small number of studies, and more work in this area would be really valuable. It's critical to evaluate this for many cases to show that machine learning is useful. In the end, right, the value of our weather predictions is not really so much, being able to predict regular dreary days like today, right? It's being able to predict the really high impact events where people have to make critical decisions. and it should be done, fairly early on in the development process. I mean, there's not a lot of point in really doing lots of fine tuning before you've checked, whether you can generalize to extremes fairly well. And as I said, more research in this area would be really useful for helping decide what kind of methods we should be using in science. And also, I mean, it's a good way to argue novelty because so few studies have really looked at extremes, and we're always pressured to do this for publishing work. So yeah, if you'd like to any more details, feel free to ask now or see the paper that I had published last year. So that brings me to the end. Thanks for listening.
Thanks a lot, Peter, for thanks a lot for the nice overview of. I think probably there's a clearly publication bias. I go to a little bit.
Thanks for the nice talk. I was wondering, when you do the QQ plots, you show usually you show first you show the map, which is a multivariate space, and then you have only one QQ plot. So is it the sum of the precipitation over the map?
It's just aggregated over grid points. That's basically a simple.
So it's not really the extreme of the extremes. You don't take the point with the most intense rainfall.
Well, I mean, it does include the point with the most intense. So it's got the most intense point on there, and that's probably dominating the tail. But it's still. But the important thing is it is showing right up to the edge of the data. So it is showing the highest point, the highest rainfall value at the rainiest point in 108 years of data. So, and if it's doing that well, I think you can be, it is good evidence that the model is actually learning to represent the tail of the events well. For the rainiest parts of the grid, at least.
And have you thought about like a multivariate diagnostic in some sense, like?
So it's like looking at separate grid points or something.
Yeah, I mean to capture not only the intensity of the extreme, but the structure of the extremes.
Yeah, that's an interesting, so like kind of correlations between points and things. Yeah, I don't think we really know a good metric for doing that. And it'd be very interesting if you do have any ideas like for things that we could look at. Because but I think that is something which is not, well, at least in weather and climate science side, I don't think it's shown very often in papers any of this kind of analysis of extremes. So it would be interesting to think more about that. Yeah.
Thanks for a very nice talk. I was wondering about your example with the Wasserstein GAN and kind of your observation that it seems to do fairly well in the tails. Do you have any idea whether that's how likely that is to kind of generalize? I was a bit surprised by it because with the Wasserstein distance, you'd think that the cost function would actually penalize you quite strongly for kind of mass that's far away from your actual data. And so I was kind of wondering if you had some thoughts on why that might be the case.
Yeah, I don't think we understand this well because these methods are quite hard to interpret, and you just really need to see more examples to tell if this is really going to be robust. I think essentially what it might be doing is because this is as a downscaling task, if this was relatively simple, it's just going from coarse resolution rainfall to fine resolution. And so what it might essentially have learned to do quite well is just, for one thing, just learn the conservation law that your sum over your little grid boxes has to equal the sum over your coarse grid boxes. And so learning that might kind of help it to generalize fairly well, whereas the VAE GAN didn't seem to have learned that. But yeah, why this happens and what kind of structures, for what kind of model structures would this generally work well? I don't think it's well known. So yeah, part of this is trying to motivate kind of people to look at this and to actually try and actually understand this.
Let's take one more quick question.
As weather events get more extreme and severe, like how do you think that ML models or systems that use machine learning components will like handle with like 1,000-year floods becoming more like 1-year floods?
Well, I don't think anyone's predicting 1,000-year floods become like 1-year floods, but yeah. But you mean like non-stationarity from climate change, right? Yeah. So I think it depends on the context, and again, it basically depends on the model's what they do for extrapolation, which is just something that needs to be studied a lot more. So if you want to do like like distant climate change many decades in the future, I don't think you can, just train a model on historical data and expect it to do well. I think the only way to really handle that is going to be to train it on model data where you've actually got simulated data from your future and you're trying to just emulate your model behavior, like in the UK rainfall downscaling case. That's kind of a key reason why we're using model data in that case, so we can actually do work for future climates. For nearer term stuff, it may be the case that these systems can actually extrapolate a bit, but it's not really been studied much. That's kind of like another problem on top of the extremes. Can we actually do, to what extent can they kind of extrapolate climate trends usefully? I don't think we know.
Thanks a lot, Peter, for the critical talk for the methods you